So, NASA is sending people back to the moon in their Artemis program as early as 2026 if everything goes according to plan. This is more than 5 decades since their last manned Apollo 17 mission in 1972, and this time, their target is the lunar South Pole. By 2030, China is planning its first manned lunar mission also to the South Pole, where it plans to construct a research outpost. As you can tell, this all seem like medium to long-term human presence on the lunar surface. But why is the moon's South Pole the main target all of a sudden? You see, back in 2018, India's Chandrayaan-1 moon impact probe with NASA's moon mineralogy mapper proved beyond reasonable doubt the existence of ice water at the southern regions of the moon. And this is a game changer, not only because water is essential for human survival, but also through electrolysis, the hydrogen and oxygen molecules can be separated to generate rocket hydrogen fuel. This means that the moon can become this giant service station that rockets can stop by to refuel on their journey into deep space exploration. This means in order to survive the harsh lunar environment, there is going to be a demand of robust supporting civil and industrial infrastructure, transportation and mining. Which brings me to today's topic, the geotechnics of the lunar surface. Before we get into the video, please like and subscribe to the channel. My name is Chido Chashe, and this is Geotechs with Clement. First thing is first, for any surface or underground construction and mining to happen on the moon, the geotechnical and engineering properties of the lunar regolith or soil should be well understood. Just as a side note, I will be using lunar regolith and lunar soil interchangeably throughout the video. From the tests that have been conducted on the moon's surface as of yet, we now know that the lunar surface is neither so soft nor so hard as was once imagined. We also know that the ranges of geotechnical properties of the lunar materials are less than those that occur in the surfacial materials on Earth. This is because of the following factors. You see, our familiar terrestrial geologic processes of chemical weathering, running water, wind, and glaciation are absent on the moon. These processes tend to produce well-sorted sediments with uniform grain sizes. On the flip side, the primary lunar soil forming process is the meteoroid impact, which produces heterogeneous and well-graded but poorly sorted soils. The three main constituents that tend to produce unusual or what is known as problematic soils on Earth are absent on the moon. There is no water and there are no clay minerals or organic materials. Lastly, the variety of minerals in lunar soil is much less than that found on Earth. In fact, many soil particles are simply fragments of rock, minerals, and glass stuck together. As a result, the geotechnical properties of lunar soil tend to fall in a fairly narrow range. The most significant variable, however, is the relative density, which can be used to estimate soil bearing capacity, evaluate pressure on underlying strata, and compute settlement and slope stability. More on that later in the video. When looking at the physical properties of the lunar regolith and terrestrial soil, some clear distinctions can be observed. We have already established that the formation process of terrestrial soil and lunar regolith differs due to the inherent weathering processes that occur. If we look at the particle size distribution, which in geotechnical engineering refers to the proportion of different particle sizes present in a soil sample, this has an engineering significance because this distribution affects various soil engineering properties like strength parameters, the compressibility, and the seismic properties. Just like here on Earth, the size distribution of lunar regolith varies from one side to another on the moon's surface. For example, the angle and intensity of sunlight and temperature fluctuations contribute to the distinct characteristics of the lunar regolith formation at the lunar poles compared to the central regions. This graph here from the Lunar Sourcebook presents the average size distribution of lunar regolith samples that were collected at different locations on the moon, including those from the Apollo and Luna 24 missions. From this graph and other sources, we can see that the lunar regolith is a fine-grained soil composed of more than 90% of the particle size is smaller than 1 millimeter and an average diameter of around 72 microns. In the previous manned Apollo missions, these fine dust-like soils even caused problems for both astronauts and machinery. It caused vision obscurity, clogged machine parts, and spacesuit joints, and even caused health problems for astronauts who were exposed. Other crucial parameters that are of interest are the bulk density and the relative density of the lunar regolith. Bulk density is basically the mass of oven dry soil per unit volume. The in situ bulk density of lunar soil is paramount because it influences the bearing capacity, slope stability, seismic velocity, the thermal conductivity of the soil, electrical resistivity, and the depth of penetration of ionizing radiation. Consequently, considerable effort has been expended over the years in obtaining estimates of this important parameter. However, one thing to point out is that the lunar explorations and landing sites for nearly all missions except the Chinese Chang'e 4 mission have been on the near side of the moon, that side of the moon that faces Earth. And this is by no mistake. For one, it just makes logistical sense. In addition, there are some practical considerations such as direct communication with Earth-based mission controls, and the clear visibility of the near side from Earth simplifies the selection of the landing site. This, however, means that we don't have much in situ bulk density data on the far side of the moon. This review paper did a great job of providing an overview of bulk densities recorded on the near side of the moon. The authors sourced information from various lunar missions, including the Apollo program, and also looked into the proposed relationships for density variation with depth and a range of suggested values found in literature. Based on the retained samples and in situ experiments conducted at the surface during the Apollo missions, empirical relations have been proposed in the Lunar Sourcebook to estimate bulk density as a function of depth. Now, considering the data obtained from lunar missions and established formulations, a representative range for lunar regolith bulk density is between 1.45 and 1.79 grams per cubic centimeter. So, what about the relative density of the lunar regolith? First, we cannot talk about the relative density before we discuss two important soil parameters, which are porosity and void ratio. You see, soil as a whole is made of solid discrete particles and open spaces in between. In geotechnical engineering, we describe the relationship between these two components as porosity and void ratio, which is the volume of void space between the particles divided by the total volume, and the volume of void spaces between the particles divided by the volume of solid particles respectively. The interchangeable relationship of the two is presented as follows. Keep this in mind because it will be important to understand the following part. Now, what does the void ratio have to do with the relative density of soil, and why is relative density important, you might ask? Let me give you an example. Let's say we have an ideal soil consisting of uniform spheres that are arranged in a face-centered cubic pecking order. Such a pecking is the loosest possible state arrangement. On the other hand, spheres could be arranged in a hexagonal close packing. this is the densest possible arrangement without deforming or breaking the particles. Hence, this ideal soil could exist in a stable condition anywhere between these two extremes. In real materials, however, these limits vary from soil to soil depending on particle size distribution, shape, texture, the orientation, and specific gravity. For a granular soil such as lunar soil, it is common to express the degree of particle packing by means of relative density, with Emax representing the maximum void ratio, which is the loosest state of lunar soil, and Emin representing the minimum void ratio, which is the densest state that the lunar soil can get. On the other hand, E represents the void ratio of soil as it presently exists, meaning the filled void ratio that falls exclusively between E maximum and E minimum. The interpretations of astronauts' boot prints and lander pad prints show that the relative density of the lunar soil is generally low across the surface. However, the in situ relative density has been found to be about 65% in the top 15 centimeters, which is medium to dense, increasing to more than 90% below the depth of 30 centimeters. Such high in situ relative densities at such shallow depth are incredible. They were not even expected prior to the Apollo missions. Just to give you a perspective on how remarkable this is, here on Earth, in pavement construction, 90 to 95% relative density is the practical limit for field compaction of terrestrial soils using heavy construction equipment at an optimum water content to act as a lubricant. Obviously, the lunar soil has not been gently sifted into place like soil on Earth as described earlier, but rather has been extensively shaken and densified, probably by some shock waves generated by impacts of innumerable meteoroids. In the preceding section, I touched on some of the lunar index properties like particle size distribution, density, porosity, and void ratio, and some other indices I didn't talk about like grain shape and specific gravity. Now, let's shift gears a little bit and talk about the important geotechnical engineering properties like compressibility and shear strength. For any safe and sustainable construction to happen on the moon's surface, it is paramount that these engineering properties and their associated geotechnical parameters are clearly derived and understood. This will be crucial for predicting how lunar structures will settle and respond to vibrations, meteorite impacts, and potential seismic events. Compressibility describes the volume change or densification that occurs when a confining stress is applied to soil. This is influenced by the initial conditions. For example, at low stress or low initial density, compression of soil results from particle slippage and reorientation, whereas at high stress or high initial density, particle deformation and breakage at the points of contact also occur. The most important parameter is the compression index, which is the decrease in void ratio that occurs when the logarithmic stress increases. This parameter gives us an insight into how much the lunar soil will deform and settle once structures are constructed on the surface of the moon. These were the compression index measured on the lunar soil samples that the Apollo 12 and Lunar 16 and 20 missions provided. Some interesting observations were made during consolidation tests of the lunar soil. If you want to know more about the soil consolidation and one-dimensional consolidation theory, please watch my previous video on the excessive settlement of Kansai International Airport. You see, the one-dimensional consolidation tests were conducted in a vacuum to mimic the lunar environment. Some bursts of gases like hydrogen and helium could be observed whenever the stress exceeded a previous maximum value. As presented in the lunar sourcebook, you can see that these spikes coincide with the increase in confining stress relative to the previous highest stress. This is significant in geotechnical engineering because such observations offer insights into how the lunar regolith behaves under varying stress levels and its stress history. On terrestrial soil, we call these stress states over-consolidation and normal consolidation. We cannot talk about geotechnical engineering of the moon without mentioning the shear strength, strength parameters, and bearing capacity of the lunar soil. You see, the shear strength of granular soil is typically defined in terms of the classic Moore-Coulomb equation. This means the strength consists of two components: a cohesive component that is independent of the applied stress and only relies on the electrostatic forces between the particles, and a frictional component that is directly proportional to the normal stress, that is, the stress which is perpendicular to the failure surface. These parameters are important because they govern important engineering properties like the ultimate bearing capacity, slope stability, and trafficability on the moon's surface. As a result, since the early days of the lunar exploration and even before the Apollo manned missions, estimates of the lunar soil cohesion and friction angles have been the object of intensive research using different methodologies and estimates. Table 9.1 in the Lunar Sourcebook presents the recommended typical values of lunar soil cohesion and friction angles, with values of friction angles in their 40s and 50s right below the moon's surface. These are incredible, if not extraordinary, strength values, considering that here on Earth, the typical in situ friction angle values of our terrestrial soil ranges between 17 and 35 degrees, depending on the type of soil and the pre-consolidation pressure. This leads us into the important general discussion of the practical consequences of this geotechnical index and engineering properties of the lunar regolith. To design and analyze structure foundation, footings, slope stability, and trafficability of the lunar rovers and other future vehicles, we can utilize the current and traditional methods that have been developed for geotechnical engineering on terrestrial geomaterials. For example, in order to design and construct the rocket's launch pads and or infrastructure foundations, the ultimate and allowable bearing capacity for static and dynamic loads on the lunar regolith can be estimated on the basis of plastic theory, since parameters of the equation like the foundation shape factor, the density of the lunar soil, the moon's gravity, and the bearing capacity factors, which are primarily dependent on the friction angle of the lunar soil, can easily be established as stated earlier. This also goes for the stability analysis of constructed and natural slopes on the lunar surface, which will be critical for open pit mining, excavation of underground structures, and stabilization of natural slopes in transportation infrastructure. In the last century, many researchers have developed dozens of numerical methods to evaluate the stability of slopes, that is, the ability of a slope to stand without support. The most common methods are based on limit equilibrium analysis of a circular potential slip surface and have been widely used in slope and embankment analysis, design, and construction. These methods can be adopted for lunar purposes, and the absence of water on the moon greatly simplifies the analysis of the slope stability. The factor of safety against slope failure can be reduced to this expression, with parameters like lunar soil density, the cohesion of the lunar soil, the acceleration of gravity on the moon, the height of the slope, and the stability number, which is a function of soil friction angle and slope angle. All these physical properties can be measured. A good example in which this could be useful is in open pit mining on the moon. The safe depth, that is, the depth up to which no slope failure will occur, can be calculated by combining values for the in situ density and the in situ shear strength, both discussed earlier in the video. then using an ideal factor of safety of 1.5, which is more than adequate for design purposes. The calculation shows that a vertical cut or a 90-degree slope could be made in the lunar soil to a depth of about 3 meters, and a slope of 60 degrees could be maintained to a depth of about 10 meters. However, things might get a little bit tricky when it comes to the embankment construction on the lunar surface. You see, in order to construct an embankment, the soil must be excavated, then transported, placed, spread, and compacted. This process of handling and manipulating the lunar soil would loosen it considerably, that even the use of mechanical compaction equipment will not be enough to compact the soil back to its original undisturbed density. This means the maximum possible slope angle of the embankment would be less than that of an excavation in undisturbed soil. As for the stability of natural lunar slopes, we really don't have enough data on that. The limited data available shows that the soil on the slope is actually somewhat weaker than the soil on the flatter intercrater areas, to the depth of about 70 centimeters. Furthermore, there is considerable evidence, chiefly from orbital photography of the moon, that slope failures have occurred on the lunar surface. In some extreme cases, the resulting debris or landslide materials have covered large areas and has traveled for many kilometers. The explanations on how this debris has been able to move such long distances are still very speculative. On Earth, slope failures are usually caused by fluctuations in the groundwater table, by erosion from running water, and occasionally by tectonic activity. On the moon, however, the triggering mechanism is presumed to be the seismic vibrations produced by meteoroid impacts. Another important aspect of lunar geotechnics is the trafficability, or the capacity of the soil to support a vehicle and provide sufficient traction to make it possible to traverse on the moon's surface. Before actual landings on the moon, it was believed that the movement of vehicles would be very difficult. So all sorts of strange-looking walking machines ended up being developed. The good thing, however, from the experience of all lunar landing missions to date, we now know that almost any vehicle with round wheels will perform satisfactorily on the lunar surface, provided the ground contact pressure is no greater than 7 to 10 kilopascals. The lunar regolith geotechnical engineering data currently available might just be enough for preliminary designs and construction on the moon's surface when used in tandem with the experience gained working on the terrestrial geomaterials, be it in infrastructure, mining, and many more industries. However, some areas still require further studies and in situ investigations in the future lunar missions. We don't know much about the K-naught value or the coefficient of lateral stress, which is a necessary and important parameter to know when designing tunnels, deep excavations, and retaining walls on the lunar surface. The gas burst phenomenon observed during the compression and shearing of the lunar soil requires further studies as well. Furthermore, there are many questions regarding the stability of natural slopes that remain unresolved. I will be following up closely on the upcoming and future lunar missions for new data and information on the moon's geology and geotechnical engineering properties. I've been your host Chido Chashe, and you've been watching Geotechs with Clemens. Please leave a like and subscribe to the channel. That will mean a lot to me. I hope you have enjoyed the video as much as I did making it. Until next time.